Hi guys, so welcome to our lecture on vectors in 3D, and today we're going to be looking at statics. So we've been working with vectors since grade 10, and we know they are indispensable in the study of physics problems, especially mechanics, both statics and dynamics. So today we're going to be looking at some simple basic sort of analysis of vectors, which include points in space, position vectors, how to work out a unit vector, and then we'll apply these to some cool problems in statics. And we'll also include what we would call the direction cosine. So hold on to your chairs and let's get moving. Okay, so let's have a look at these coordinate systems. They're absolutely important doing mechanics. It's frightening to think of students working out problems or solving problems in mechanics without even alluding to a coordinate system. So the picture on the right is a 2D coordinate system. You're familiar with this from school. Horizontal axis called the x-axis. Associated with the x-axis, the direction there we'll call the unit vector I, and then in the y direction, the unit vector j. If you look at the blue point, P1, it has coordinates 3, 4. And so we can actually establish from the origin, this point over here, coordinates 0, 0, right? That's what we would choose as a local origin. And we can put through that 2-point P1 a vector that looks like this. Well, ought to look like this. Okay, so what's the direction of that as well? So if we want to actually write this vector now in Cartesian form because it's in 2D, it's something I plus something j. What are those some things? Well, very quickly we can write, let's call that vector r. So the vector r, which is that blue line, is going to be the coordinates of P1. X coordinate is 3 minus 0 because we are the tail of that vector is sitting at the origin 0, and that will be I, plus 4 minus 0 j. So the vector r, or what you would call OP if you wanted OP1, is 3i plus 4j. That's the Cartesian form of that vector. Now, no prizes for guessing. What would be the vector, say R2, if I want to call it, which is a vector pointing away from the origin towards point P2? Well, it's the coordinate of P2, the x coordinates will be minus 1, minus 0i, plus, watch this, minus 3 minus 0 j. Simplify that. That's minus I minus 3j, and that's the vector pointing from the origin towards P2. Easy peasy, nothing to it. Now let's get to the coordinate system if you're looking at the one on the right, and that is in 3D. So associated with these axes, we're going to have 3 unit vectors. Usually I points in the x direction, j in the y direction, and k, of course, in the z direction. Remember what a unit vector is. At its magnitude 1, it just provides the direction. Now what's also interesting is identifying these planes. They'll help us also determine the coordinates of points. So for instance, if you look at, I like to think of them as the wall and the floor. So if you look at the YZ plane, that one, it's the one that's perpendicular to that screen, so it's the back wall. The floor of the system is the XY plane, and the side wall, because the x-axis is pointing out towards you, is the ZX plane as we see it over here. So we think of that in 3D, and then obviously our origin is sitting there with coordinates 0, 0, 0. Right, let's take a closer look at what we would now call position vectors. Okay, position vectors, very, very important, as I said. And in this case here, we have a vector, which is the vector r. You notice there r with the little arrow on the top, or arrow r with an underscore would still mean vector. Without the underscore or the arrow on the top, that would refer to the magnitude of the vector. So the vector is pointing away from the origin with coordinates 0, 0, 0 towards a point 3, 4, 1, 0. So that position vector, if you want, let me just use underscore, would be 3 minus 0. It's going to be 3 components plus 4 minus 0 j plus 10 minus 0 k, and so that's obviously 3i plus 4j plus 10k. Now what is the magnitude of that vector? What is the size, the length of that vector? So the magnitude, watch the units, but the notation, that will be 3 squared plus 4 squared plus 10 squared, and that ought to be 9 plus 16 plus 100, and that's the root of 125, whatever those units are. In this case we're using arbitrary units here, which turns out to be about 11.18 units. There you have it, the vector itself from the Cartesian coordinate system and its magnitude. Also notice the direction. The direction is very important. If I had to reverse that arrow end pointing in the opposite direction, then of course we will also introduce a negative sign, and I think that's quite clear. Okay, now let's get to the point of a unit vector. What is a unit vector? Well, the same vector as the previous slide, if you remember. That vector had components 3i plus 4j plus 10k. Do you remember the magnitude of the vector? Root of 125. How do we establish a unit vector or create a unit vector from this vector r? The unit vector, it's like that, would be the vector itself. Oops, how did I do that? That's not good. Well, that was deliberate, let's put it that way. Let's check whether you're awake. The unit vector is actually the vector itself divided by its magnitude. The vector itself divided by its magnitude, so that would be 3i plus 4j plus 10k all over the square root of 125. Now it is very simple to verify that the magnitude of this vector, please check this, the magnitude of the vector is exactly 1. Okay, and I think that's extremely important to know as well. So the unit vector just provides us with direction. Okay, so here's a little nifty problem that I've found. That is, determine the resultant force vector in Cartesian form and calculate the resultant magnitude of the two vectors shown. So there you have two forces acting on this little hook. Is it a hook? An eye, it's an eye, something like that. So force F1 pulling in that particular direction, 60J plus 80K, X component is 0, and then F2 has 3 components. Just keep an eye on the coordinate system. That's also very important. So X pointing towards us, Y there, and Z obviously pointing up in the vertical direction. So how do we determine the resultant force? The resultant force, firstly, vectorially, let's put it that way. So the resultant force, let's write that as R, vectorially. That's a nice word. F1 plus F2. So you'd add, okay, let's just write this out. And watch how I'm going to write this out. It's going to be 0i. You agree with me? 60J plus 80K plus 50i minus 100J plus 100K. Now, you can add components because they are really nothing more than scalars. So 0 plus 50 is going to give me 50i. 60 minus 100 is going to be minus 40j, and then no prizes for guessing. That's 180k. So the next part of the question, that's the resultant vector. How do you find its magnitude? Its magnitude is very simple. It's the root of, you would have guessed, 50 squared. I like to include the minus sign, although we're squaring it, doesn't really matter. 180 squared, whatever that is, that's just going to be a very simple number. In fact, when you're doing this, do not forget to take the square root at the end. So 50 squared should be 2,500, right? And then you got 40 squared over there. That should be 1,600. Is that right? Positive. And this double check that 180 squared is 32,400. Plus 2,500, 34,500. So that's just the root of 34,500, and that should be in pounds. Yeah, there we have it. Simple, easy peasy. Let me write that down. Easy peasy. This is a beautiful question. Have a look at this. There's this 100-pound force acting at a point there. It's almost a hook or something like that. At the origin, we place the origin there. Again, notice our axis x, y, z, x pointing towards us. And the question is, we're given the magnitude of the force. That's interesting. We now want to find out this force in Cartesian form. So when we see that, we want to write the force F as Fxi plus Fyj plus Fzk, where Fx, Fy, and Fz are the components in each of their respective directions. Absolutely cool. A picture is not very, very clear, but you want to look at this very carefully, because this picture is actually a bit misleading because it's so badly. That 60 degrees there is between the vector and that point there. So one can think of, can I draw this in yellow, this line as a shadow of that force F onto the xy plane. Okay, so if that angle is 60 degrees, think of that light blue triangle. You must agree with me, sometimes it's difficult to see these things, that this is a right angle triangle, by the way. And so we can work out Fz almost immediately without thinking. In fact, if it's using up 60 degrees here, then obviously this angle, I don't know if you see it, is 30 degrees. And so we can project the force F onto the z-axis. So straight away, without even thinking, we can write that Fz along the z direction here. That should be F, which is the magnitude F, cos of 30 degrees. So we're projecting onto the z. That's 100, and cos is, if you remember, root 3 upon 2. So that's 50 root 3 Fz. Okay? You see, it's a scalar. Please take some time, have a look at this very carefully. Now, here's the tricky bit. The tricky bit is, how do we find the x and y components of this vector? If you look at the vector f, which is that black line, arrow that you see there, I said imagine yourself, this is in 3D, and you're standing above this vector with a light shining down onto the arrow. It should project a shadow onto the xy plane, and that shadow is that yellow line that you see there. So let's work out the component, that shadow, of that 100-pound force. So I'm going to make this crazy claim, and hopefully you agree with me. Well, before I do that, I want to call that yellow line FH. Please tell me whether you agree with this. FH is equal to the magnitude F of that force, which is 100 cos of 60 degrees. Look at the light blue triangle. So that becomes 100 cos of 60, we all know, is a half, so that becomes 50. Leave out the units for now. That's FH, which is the yellow line. That's the shadow. Now I want to take that shadow, which is the yellow line, and I want to rotate it onto the x-axis. Okay, so that's basically what I want to do. I want to rotate that shadow onto the x-axis. And so basically what we are doing, when I say rotate, I mean take this and cast it onto that there. So that angle is 45 degrees. So please tell me whether you agree with this one. The x component is FH. You're rotating by an angle of 45 degrees. That's 50. And what is cos of 45? 1 over root 2. So eventually I have 50 over root 2. That's x component. And it's a positive x component. Now, what's happening with the y component? Well, we know the y component should lie in and point in the negative y direction. So the y component is going to be minus, take the yellow, and I'm going to claim that that is 45 degrees. Which 45 is that? Why am I screaming? If this angle is 45, then the remainder there should be 45 as well. So that's going to be minus 51 over root 2, which is minus 50 over root 2. And finally, getting a hold of myself here, the force F is Fxi, and where's Fx? It's 50. So what have we here? We have an elastic band is attached to points A and B. So here we go, point A there, point B over there. Determine its length and its direction measured from A to B. Length and direction. So if you have a look here, we haven't explicitly given the coordinates of A and B. It's usually the case. So we've got to figure out the coordinates of point A and B. In order to do that, we need to establish our sort of orientation of the axes. So notice there's X coming out towards us, there's Y, and then Z pointing up in that direction. So having said that, let's look at the coordinates of A. So let's look at the X coordinate of A. The X coordinate of A would be along this axis over here, and straight away we can see it's 1 meter away from the origin. That's very important. Now, look at the Y coordinate. I always like to think of the point A being part of the wall. So the rubber band is attached to the wall, can't be in midair. So it's actually in the XZ plane. And the fact that it's in the XZ plane means Y is 0. And the last coordinate is Z, and you can see that sits below the XY plane. So be careful here. The Z coordinate is going to be minus 3. And now I'm going to have a look at the point B. It's quite easy. Watch here, there's the origin, but B lies at the back, if you think of it, on the back wall, so to speak. So its X coordinate is going to be, that's right, minus 2. Y coordinate would be the one sitting over there. That's going to be plus 2. And then the Z coordinate, again, no prizes for guessing here, would be 3 meters above the XY plane. In order to work out the length, use the distance formula. So the length is going to be the square root of, you remember this, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And let's have a look. So x2, we can take any one to be x2. So we go minus 2 minus 1 squared there. There. And the next one would be plus 2 minus 0 squared. And the last one is going to be 3. Be careful here. Minus 3 all squared. So minus 2 and minus 1 all squared. That looks like 9 to me. 2 minus 0. That's going to be in squared. It'll give you a 4. Be careful here. 3 minus 3. I almost said 9. That's going to be 6. 6 squared is 36. 40. Here. It's going to be plus 7 because we're thinking of length. So it has to be plus 7. Now the second part of the question is a very simple one. We want the vector pointing from A towards B. So the head is at B and the tail is at A. So the vector, I like to write as RAB, is going to be the coordinate of B minus 2 minus 1. Watch this. I plus 2 minus 0 j, and the last one would be 3 minus 3. I like to write that in the exams like that, so the examiner can actually see, even if you made a mistake, where you went wrong. So minus 2 minus 1 is minus 3i. There's no square here. 2j, and 3 minus 3 is plus 6k. And that's your position vector pointing from A to B. Absolutely simple, straightforward. Cool stuff, man. Yes, this is a really important question. I think it actually forms the basis of this entire section that we're looking at, and that is how to express a vector in Cartesian form purely out of the coordinates. I'm not talking about a position vector. I'm talking about something like a force. So if you look here, a guy pulls on a cord and it gives you the magnitude of the force is 70 pounds. You want to write this as a Cartesian vector and also determine its direction. So have a look very carefully. You're pulling at point A up there. So obviously it's going to be directed away from A towards B. That's the first thing. The next thing we want to look at is we want a position vector pointing from A to B, which means we need the coordinates of A and B. In order to do that, let's establish our coordinate system. There's X, there's Y, and Z point vertically upwards, which is in the K direction. Where's our origin? Always look for the origin. Locate the origin. There's it sitting down here. So it tells me straight away from the setup that point A is sitting on the Z axis. So the point A would have coordinates 0, that's the X, 0 for Y, and 30 for Z. What about the coordinates of B? A little tricky here, just be very careful. The coordinates for B, if you have a look, that 12 means something. It's just not sitting there for nothing. It's 12 units away from that wall, so the X coordinate will be 12. Be careful of the Y coordinate. It's the other side of the origin, so it'll be minus 8, beautiful, and 6 feet above the XY plane, so that's Z. So if I want my position vector RAB, remember it's from A to B, pointing towards B, it'll be 0. No. It's the coordinates of B minus the coordinates of A. So it's 12 minus 0i plus minus 8 minus 0j plus 6 minus 30k. Let's simplify that. That's 12i minus 8j. 6 minus 30 is minus 24. Okay, that's the position vector. Most students, what they do is they will take the 70 pounds and multiply it by RAB, and you could never be more wrong. And what you want to do is create a unit vector, EAB. How do we create unit vectors? We take the vector RAB and we divide by its magnitude. So there we have, it's 12i minus 8j minus 24k all over. How do we find the magnitude of RAB? Correct. 12 squared plus minus 8 squared plus minus 24 squared. You can do that with a calculator. I don't own a calculator, never did. And so now the force F directed from A to B is given by the magnitude of f times this vector that we just found, EAB. It's 70 times EAB. Of course, you will simplify. You would find out what EAB is, and you'll substitute in there, and you'll see it'll be in the form of a Cartesian vector. 70 times something I, 70 times something j, plus 70 times something k. Sweet, simple. Please review this problem before going on to the next one. So what have we here? Same old, right? Just like the previous one, except now we've got 2 ropes instead of 1. So yeah. The roof is supported by cables as shown in the photo. If the cables exert a force of FAB 100 newtons, FAC is 120 newtons, that's basically the magnitude of the forces. We want the resultant force acting at point A due to these 2 ropes. So the ropes are pointing away. So obviously the force is directed from A to B and then from A to C as well. And we want the resultant force. The resultant force obviously in vector form is nothing more than FAB vector plus FAC vector. I'm not saying the resultant is 120 plus 100, which is 220 newtons. That is wrong. So in fact, let me just write this on the side so you understand what I'm saying. So I'm saying that the magnitude of the force R is not equal to the magnitude FAB plus FAC. Do you see the difference between what I wrote in red and what I wrote in purple? If you haven't, call me or email me. Right, now let's have a look very carefully here. Let's try to establish the coordinates of points A, B, C. Again, take note of your axes. There's X, there's Y, and there's Z. You've got the XY plane, so let's look at coordinate A firstly. Coordinates of A, it's sitting right at the back on the Z axis, so straight away we know that X will be 0, Y will be 0, and Z will be 4. Please check that, because you can see that A is sitting on the wall, it's mounted on the wall. Look at B. B is at the bottom here. It's 4 units, that 4 units away from the wall. It's obviously sitting on the x-axis, so it's sitting on the x-axis. We know straight away that y must be 0 and x must be 0. And finally, point C. Again, 4 units away from the wall, 2 units away from the x-axis, this 2. And of course, it's sitting on the xy plane, so its z coordinate's going to be 0. And there we have it, as simple as that. So if I want the force FAB, I need to find the position vector RAB. So remember, it's the coordinates of B minus the coordinates of A. And at this point, you should be able to do that. So it's 4 minus 0, which is 4i, 0 minus 0. I'll write this as 0j. And 0 minus 4 is minus 4k. While you're there, I want you to write down the unit vector EAB. It's the vector RAB all over, right neatly, all over its magnitude, RAB. So you're going to get 4i plus 0j minus 4k. And this is going to be 4 squared plus 0 squared plus minus 4 squared. That will be a 4i. Maybe we can drop the other one now and just write minus 4k. And you've got 4 squared and 4 squared. That's going to be 16 and 16. That's 32, which is 16 times that. So it'll be 4 root 2. And you can simplify that. So you can see where that is going. Similarly, if we want RAC for FAC, so what is RAC equal to? It's the coordinates of C minus the coordinates of A. So 4 minus, there's that 4, there's that 0. Please check where you are. This is a beautiful blue, by the way. 2 minus 0 is plus 2j, and 0 minus 4 is minus 4k. What else are we going to find? EAC. What is EAC equal to? Well, it's the vector, whoops, not that. Be careful. It's the vector RAC all over its magnitude. So what we just found was 4i plus 2j minus 4k all over the magnitude, which is 4 squared plus 2 squared minus 4 all squared, and 4i plus 2j minus 4k, squeezing things in there. That's 16 and 16, that's 32, and 4, that's 36, and root of 36 is going to be 6. So here we have it. 2 position vectors, 2 unit vectors. No prizes for guessing how we're going to write out the force FAB and FAC, which we're going to take up in the next slide. Okay, so in order to finish up the problem, it's very, very simple now. We need to write FAB and FAC as Cartesian vectors. So we got FAB is now the magnitude, which is 100, that was given to us, times the unit vector EAB. So please check out the previous slide and you'll be able to write down FAB. The next thing we look at is FAC. That is 120 times EAC. How do we work out the resultant? Well, it's pretty straightforward, isn't it? The resultant is nothing more than FAB plus FAC. And your final answers would be, you know, my famous line, something I plus something J plus something K. So take a look at that. Pretty straightforward. And to work out the magnitude, then it's really nothing more than, if you take the magnitude of this vector, it's the root of each of these brackets squared, isn't it? The sum of these things squared. So yes, having problems, just email me, and yeah, we can discuss this at a closer level. But it's a straightforward problem, and I think it's a cool problem in actually knuckling down how you write vectors from the magnitudes and the unit vectors. So very good problem indeed. Okay, so here this is a very important concept when it comes to 3D vectors, and that is something called the direction cosines. Absolutely useful when doing calculations. Now, what are the direction cosines? So have a look at this picture. Not really clear, but you have this vector A, this beautiful blue vector that you see there, the vector A, and then you have associated with that these angles alpha, beta, and gamma. So it doesn't take a genius to realize that the angle alpha is with the x-axis and the vector, the angle beta is with the y-axis and the vector, and then the angle gamma is with the z-axis and the vector A. So the direction cosines are defined as such: cos of alpha, x-axis and the vector is ax over the magnitude of the vector A, cos beta is ay over A, and finally cos gamma is az over A. So in a way, the direction cosines actually gives you the components of the vector, because if you have a look, for instance, ax is magnitude A times cos alpha, ay is magnitude A times cos beta, and az is magnitude A cos gamma. And there's a beautiful result, which is something that you want to actually prove, and that is cos squared alpha plus cos squared beta plus cos squared gamma equals to 1. It's a lovely, beautiful proof. Please have a look at it and work through it. I always believe if you work through a proof of a theorem or result on an identity, you'll remember it for the rest of your life. So that's your homework, please. Very, very important. Here's a really cool question, guys. If you have a look here, you can see straight away you've got a vector, or you've got a force of 200 newtons. That's the magnitude. So I'll actually write down the word given. It's useful in the exams. The magnitude of F is 200 newtons. And then if you have a look very carefully, no prizes for guessing, theta x is known as alpha here, and theta y, be very careful in the way it's between the y-axis and the vector is 60 degrees. And then theta z is 45 degrees. Now, we need to write this force F in Cartesian form. What does that mean? Well, Cartesian form is take this force F, write it as something I plus Fyj plus Fzk. But what is Fx? Well, recall cos theta x is Fx over the magnitude of F, which is Fx and the magnitude was 200. Cos theta y, Fy over the magnitude of F, and that is Fy over 200. But what is cos theta y? Be careful, it's cos of 60 degrees, which, if you remember, was a half. And then the last one, let's just squeeze it in here, cos theta z. You can see where this is going. Now it's becoming a boring problem. Cos theta z is Fz over magnitude of F, so you got Fz all over 200. But what is cos theta z? That's cos of 45 degrees, which you will remember from school is 1 over root 2. So take a quick look. Let me mark this in this beautiful red. We do have Fz. We do have Fy. The problem is we don't have Fx. Why? Because we don't have theta x. So give you a few seconds to think about this very carefully. How do we get theta x? Because once we've got theta x, we've got fx. And once we've got fx, come guys, think about that. We've got f in Cartesian form. Let's put smiley face. But for the moment, we don't have theta x. But you'll remember very quickly something very interesting, something new that I put out there today, and that is cos squared theta x plus cos squared theta y plus cos squared theta z equals to 1. Well, we know that. We know that. So the only unknown would be theta x. And once we've got theta x, this problem is solved. I want you to have a look at this problem. Do not look at my solution. Write out your solution. Map out the steps properly, and finally write down f as something I plus something j plus something k. This is such a cool, awesome problem. It's too easy for the exams though. So happiness lasts for a few seconds here. It's gone, watered down, weathered away, fell into a black hole. Anyway, let's look at the next problem. Okay guys, this is a really cool question. Here you've got two forces acting on the hook. Captain Hook, specify the magnitude of F2. We know nothing about F2 here. And its direction coordinate angles, so that F2 and F1 that you see acting here, their resultant acts along the positive y-axis. So the resultant of those two forces acts along the y-axis. And the magnitude of that resultant is 800. So it's interesting. So that I know from that statement that the magnitude R is going to be 800 times J. Please check that out, especially in this very last line, right? Along the positive x-axis, magnitude 800. So it's telling me that F1 plus F2 must equal to, obviously, R. That's vectorially we write that. It makes sense. The force F1 is very simple. Its magnitude would be 300, and then you've got to take the cosine direction, cos of 45 degrees, which is that angle. And the next thing we want is 300 magnitude, cos of theta y, and theta y is 60 degrees. Check that out. And the last one would be 300 magnitude, cos of 120 degrees. That's just for the force F1. Now F2 would be F2xi plus F2 yj. Sorry, this doesn't make sense. I've got to put my unit vectors there. Naughty, naughty, naughty. They're not scalars, so they're vectors. And then the last one would be F2zk, all equals to 800j. Get that? And now it's pretty obvious what we're going to do. Bad boys, what you going to do? Oh, slightly distracted there. So compare. There's I, and there's no I on the other side. So it tells me if you compare the I components, you're going to get 300 cos 45 plus f2x must be 0. If you look at the j components here, you got to be careful. 300 cos 60 degrees plus f2y, oh, be careful there, equals to 800. And the k component, the very last one, is 300 cos of 120 plus f, right, neatly equals to, no k components on the right hand side, equals to 0. And what do you have? What do you have? What do you have? Equation 1, equation 2, equation 3. How many unknowns? 3 unknowns. Problem solved. Yes, 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 yes. And to work with the magnitude, come on, that's pretty straightforward. It's the root of f2x squared plus f2y squared plus f3z squared. I'm falling asleep. I need something more challenging, people. Okay, guys, so here's a really cool question. You know, you have a single force and you're not given all the direction cosines. You're given little bits and pieces of information. You've got to tack them all together, weld them all together to get the magnitude of the force. And once you've got that, you've got to determine the other 2 direction cosines, and eventually you can write the force as a Cartesian vector. So I'm going to leave that as homework for you. It's really cool. I've completed the solution in the next slide. Don't take a peek until you do this by yourself. We don't want you becoming too dependent on me. So yeah, have a go at this, get this right, tap yourself on the shoulder, and then we'll move on to the projection of forces onto lines. Awesome section indeed. Can't wait to get there. Cool stuff, guys.